PQNK, the Pristine Organic Farming System. Beyond the timeline, reframing the transition to regenerative agriculture through the lens of soil life. PQNK, cultivating sustainable tomorrow through regenerative agriculture. Busting the myth, it takes 3 to 5 years to establish a system. A common refrain in regenerative farming circles is the need for patience. It takes 3 to 5 years to establish a system. This timeline is often offered as a comfort to new practitioners facing initial challenges. However, this well-intentioned axiom is fundamentally misleading. It misrepresents the actual biological processes at work and can lead to misplaced interventions. A more accurate and empowering perspective is not based on the calendar, but on the rapid and resilient nature of soil life itself. The flaw in the calendar-based model. The conventional 3+ year model implicitly suggests that the benefits of regenerative practices, like no-till, mulching, and ending chemical applications, are slow to accumulate. This view risks portraying the soil as an inert substance that slowly improves, rather than a living ecosystem waiting for the right conditions to explode into activity. This mindset can lead to errors in problem solving. When a crop struggles in its first or second year, a farmer might assume the system is simply too young and requires a familiar input-based solution, potentially undermining the very biological processes they are trying to foster. The yogurt principle: life fills the niche instantly. A more scientifically sound analogy is that of making yogurt. When you provide sterile milk at the correct temperature and introduce a starter culture, fermentation begins almost immediately. The process isn't slow, it's rapid and exponential. The same is true for soil. The moment a farmer provides the correct conditions, by ceasing tillage, which destroys fungal networks and oxidizes carbon, ending biocidal chemical applications, and providing a carbon source, mulch, they send a clear signal to the soil biome. Life responds with breathtaking speed. Bacteria and archaea can double their populations in a matter of hours. Fungal mycelium can expand geometrically across a field in days when food and oxygen are present. Earthworms and other macrofauna will quickly migrate into a newly hospitable habitat. Protozoa and nematodes, with life cycles measured in days, will rapidly proliferate to prey on the new bacterial and fungal blooms. The transition does not begin in year 3, it begins in hour 1. The microbial engine of the soil is kick-started immediately. From timeline to benchmark, assessing function, not age. If the transition is instantaneous, why do we sometimes see a lag in system resilience or productivity? The answer lies not in the presence of life, but in its maturity and functional balance. The shift in thinking is crucial. Stop asking how old is the system? And start asking, is the system functioning yet? Even with rapid colonization, ecological succession is a process. The initial explosion is often dominated by our strategist, fast reproducing, bacteria. Achieving a resilient, mature ecosystem, one with a robust, diverse, and balanced network of fungi, especially mycorrhizal fungi, bacteria, and higher trophic levels, takes time. Key functional benchmarks include 1. The fungal bridge. Mycorrhizal fungi are critical for water and nutrient exchange, particularly phosphorus and zinc. Their extensive, stable networks take longer to establish than bacterial populations. 2. Humus formation. While microbes immediately begin decomposing organic matter, the process of creating stable humus, which builds soil structure and cation exchange capacity, CEC, is a complex, multi-step biological sequence. 3. Legacy issues. Past management like compaction, chemical residues, or extreme biodiversity loss can create temporary bottlenecks, slowing the establishment of a fully functional web. The ultimate benchmark: resistance to inundation. The most critical functional benchmark for a transitioning system is its resistance to waterlogging. A soil without stable organic matter and the glues produced by microbes, like glomalin from mycorrhizal fungi, is a collection of particles. It compacts easily and, when saturated, becomes a lifeless, anaerobic slurry that suffocates roots. A functionally mature soil is an ecosystem engineered to prevent inundation. Aggregate structure, fungal hyphae and microbial secretions bind mineral particles and organic matter into stable aggregates. Pore space, this structure creates a vast network of pores, macropores for water infiltration and drainage, wormholes, root channels, and micropores for water retention. The sponge effect, this porous, aggregated soil acts like a sponge. It greedily absorbs intense rainfall, dramatically reducing runoff and ponding, and then holds that water in its structure for plant use, resisting both drought and flood. Therefore, the question for the farmer is not how old is my system? But how quickly does my soil absorb a heavy rain and then drain to a well-aerated state? The PQNK Blueprint for Immediate Ecosystem Function. The PQNK, pronounced picnic, which stands for Paedar Qudratti Nizam Kashatqari, meaning the Regenerative and Sustainable Pristine Organic Farming System, framework, based on natural ecosystem science, reveals that the transition is not about waiting but about acting correctly to instantaneously create the conditions for life to flourish. The calendar is irrelevant, the correct architecture is everything. The following steps are not sequential options but an integrated, non-negotiable system. This is the architecture of a flood and drought-proof farming system. 1. Break the hardpan. This is the first and most critical intervention. A compacted layer prevents water infiltration and creates an anaerobic, lifeless zone beneath the surface. Shattering this hardpan is non-negotiable to restore the water infiltration and gas exchange that nature designed. It re-establishes the aerobic foundation upon which all soil life depends. 2. Form raised beds. Immediately after deep loosening, form permanent raised beds. This is the primary physical defense against soil inundation. Raised beds ensure perfect drainage, preventing water from ever pooling around plant root zones. They create a defined, optimal environment for life to thrive, separating the productive zone from potential waterlogging. 3. Cultivate with cover crops. On these newly formed raised beds, cultivate a diverse mix of cover crops. Their roots are the primary tool for building soil structure, naturally opening pores, and feeding the entire soil food web. This living root system holds the bed structure together. The core principle, when terminating the cover crop, do not uproot it. Leave the roots to decompose in place. This creates a self-sustaining cycle where the roots become the food source for the biology they helped establish. 4. Apply thick organic mulch. Blanket the beds with a thick layer of organic mulch. This manages the microclimate, maintaining the moderate soil temperature, 13 degrees Celsius to 26 degrees Celsius, essential for peak microbial activity and conserving adequate moisture. The mulch is not just a covering, it is the constant food source that fuels the microbial engine, creating an ideal environment for microbes to flourish and build stable humus. 5. Commit to no-till planting. Once the beds are established, all subsequent planting must be done with a no-till planter. This principle protects the capital built by steps 1 to 4. It ensures the fragile soil structure, pores, and critical fungal networks are never disturbed, allowing the ecosystem to mature and reach its peak function and resilience. 6. Eliminate external inputs. From day 1, halt all agrochemicals. A system built on the previous 5 principles will generate all necessary nutrients from within. Synthetic fertilizers and poisons destroy the very biological life this system is designed to foster. They are incompatible with a functioning ecosystem. It is crucial to understand that any production process that inundates soil with water, disturbs soil through tillage, or leaves soil bare without organic mulch cover does not qualify as natural ecosystem science for production agriculture. A practical case study, the waterlogged okra revisited. Consider a first-year PQNK, Paedar Qudratti Nizam Kashatqari, okra farmer with healthy plants but no fruit set after excessive rain. The PQNK diagnosis: The problem is not the age of the system or a nutrient deficiency, but rather inundation and oxygen stress due to underdeveloped soil structure. The plant, in survival mode, aborts reproduction. Revised Biology First Recommendations. 1. Immediate action: stop any irrigation. Consider strategic pruning to reduce the plant's water demand and stress. This addresses the root cause, oxygen starvation, without inputs. 2. Reframing inputs: a foliar spray of boron zinc should not be a default fix. It should be viewed as a diagnostic tool or a temporary biological crutch. If the soil ecosystem is already functionally mature, the spray is unnecessary. The problem is oxygen, not nutrition. If the fungal network is still nascent and unable to mobilize sufficient zinc, a mild foliar application could act as a bridge during a critical reproductive phase, supporting the plant until the soil web is fully operational. 3. Accelerating the process: long-term solution. The only true fix is to accelerate the development of soil structure. This is done by maximizing living roots, keep roots in the ground to build organic matter and create biopores, mulching heavily, provide constant food for the soil engineers, worms, fungi, bacteria, that build aggregates. Avoiding compression: use furrows to pass through the field, never work on or drive equipment on the beds, especially on wet soil. Conclusion: the farmer is ecosystem architect. This refined understanding is liberating. It moves the farmer's role from a passive waiter hoping time will fix things to an active ecosystem architect. The goal is not to manage inputs but to steward conditions: no inundation of soil with water, no tillage, no poison, constant mulch, and biodiversity. The primary goal is to build a soil structure that resists inundation and maintains aeration. The biological transition is rapid. Our trust in it must be equally rapid. By focusing on creating the habitat that builds the sponge, and functionally assessing the ecosystem's health by its water infiltration rate, we align ourselves with the inherent intelligence and speed of soil life. This is the true heart of ecological agriculture, not just growing plants, but building a resilient, life-filled soil that protects those plants from stress, and unleashing the life that is already waiting for the right conditions to thrive.